other people. I did not put all references. So this theory, the point is that this theory is extremely well established, checked by many people, and we don't have any reasons to doubt. So what does it say? Yes. Okay. So we are studying power transferred from electrons to phonons. We assume electrons are at some temperature TE, phonons at some temperature T phonon, and then you have this kind of expression for this power. And there is a reason why the expression should be of this form. But there is no reason why this should be a power, why this function should be a power law. And it's not a power law. It's a more complicated function. It's an integral. So in a normal metal, it has this simple form where f lambda of x, so lambda is phonon polarization, longitudinal or transverse. So it's a function that was written already by Schmidt. So you have two of them, longitudinal and transverse. So they are a little bit bulky. There are like some arctangents, but it's an analytical function that you can write down and calculate this integral. And you see that, so V lambda is the speed of longitudinal phonons or transverse phonons. And T lambda is the crossover temperature, so velocity of phonons, and L is the mean free path of electrons. So you look at low temperature asymptotics, you get T to the power 6. So low temperature means that your phonon, so the phonon wavelength that is emitted in this relaxation process is whether it's larger or smaller than the electronic mean free path. So low temperature means that you have long wavelength phonons, and so then you have T to the power 6. And if you go to high temperature asymptotics, you have T to the power 5 for longitudinal phonons and T to the power 4 for transverse phonons. The coefficient in front of here, it does not contain mean free path. So if you take the limit, clean limit, mean free path to infinity, you are left only with this T to the 5. And so this is the essence of what was said here. That we have, even when you are supposed to be in the diffusive limit, for some reason, the experiments agree better with this T to the 5, which is the clean. Okay, so then I decided, yeah, so that was for the normal metal, and for superconductor, it's a little bit more complex because you have already extra ingredients. You have your weapon in the quasi-particle density of states. You have some matrix elements, Golubov, but so basically this is a decoration of this integral. You have extra stuff here, but the essence is the same. Like you have again the same functions that enter in this superconductor, and the same that will be achieved. So this would give you, if you are in the superconductor, quasi-particle which is slightly above the gap, you have different powers for relaxation time of this quasi-particle. So, and this is why it became kind of important recently because of the qubits in superconducting resonators, and people worry about quasi-particle dynamics in the qubits. So this is why this old science is still interesting. So I decided to, okay, we have this statement that there is a problem, there is disagreement with experiment. So I tried to look for experiments. So last Friday I did some literature search in the old-fashioned way with artificial intelligence, and I will show what I saw. So this is probably the first paper, the most well-known one. So they have studied this relaxation of power and electron temperature, which is overheated. So and they fit the slope, and they see temperature to the power 4.87. This is not 86 and not 88. There is no case. Yeah, this is very important. Okay, then artificial intelligence drew my attention to this paper by Gershon. And this is, so it's equal to the 5, but this is thermal conductance. So this is actually diffusively. Then there is a nice paper by three gentlemen. Okay, so here, every time you need to estimate, so you need to get an idea of your mean free path, and then you need to estimate the crossover temperature and see where you are with respect to the crossover temperature. So here, they did several samples, different metals, but so these are wires, so this usually, so they don't give any number for mean free path. Independently, they just say each of the order of wire thickness. Okay, so these are the crossover scales. And they see, sometimes they see power 5, sometimes they see power 6. This is from Yuka Pekola's group. So aluminum, both superconducting and normal. They can make the same sample, so they take the same sample, put magnetic field, and it becomes normal. And well, looks like power 5, temperature sub-Kelvin, you see. So this, so TC is, so they use TC, so this is well sub-Kelvin. Okay, this is more recent. So here again, T over TC, so temperature are sub-Kelvin, and the fit is, so you see this, the limit to the 5. This is more recent, so they have particle lifetime is a function of temperature, and they have theoretical curve, and this is clean, so they use superconducting cooling for clean in the clean rings. Okay, so I looked at all of this and then this problem, and while preparing this, I came up with maybe an answer. So that's what I want to show now. So I just said, okay, let me plot this function for pedagogical purposes. So I plot, and here we have t to the 6. This slope is t to the 5. And here we have something that is more like t to the 4-ish. So where does this thing come from? So you see, there is, so when we have this crossover scale, so if I plot everything in units of this crossover scale for transverse phonon, then the shape of this curve, it depends only on the ratio of the velocities, longitudinal to transverse. Okay, so this is for 2.1, which is copper. But they all are pretty similar, yeah? So in different metals, this ratio is maybe 2, maybe 3. So where does this t to the 4-ish is come? Well, we have this high temperature expression. So there is overall prefactor, but the two terms here from longitudinal and transverse phonons, they contain this coefficient. And longitudinal to transverse velocity, so we all know that longitudinal is always higher than transverse, but it should be, so the ratio, it's actually bounded. So from elasticity theory, if you open Landau Lifshitz, the ratio VL over VT should be bigger than square root of 2. And this means that this coefficient in front is at least 10. And in practice, when the ratio is 2, then it's more like 50. And this means that this 4 t to the 4 intermediate asymptotic slide, it's visible here. And when you have t to the 6 here and something t to the 4-ish here, then of course you have t to the 5 somewhere in the middle, and it goes over a decay in temperature. So to distinguish the power law, you need to have at least a decay in temperature. And if we make a step back, let's see. So you see this basically from okay. There is this data set which does not describe, is not described by the theory, but the rest there is less than a decay here. Here, well, factor of 4. Here, half a decay. Here. So this data is more extended. So here are almost 2 decays, and this is where you actually see it. And here again, there is not well, okay, there is maybe decay here, a bit more here, but this is where it starts. So that's my suspicion that this disagreement like is actually based on this strange region of this curve. So it's not a power law, but it's a series of crossovers. So most experiments are here where none of the power law strictly applies, but if you don't have wide enough range of temperatures, you can have something resembling a power law, and if you are more here, you get 5. If you are more here, you get 487. So this is what so I realized this just a couple of days ago when preparing this.
Where's the mean free path?
Sorry?
I mean, this should be in the desired limit, so it should depend on the mean free path. So
yes, exactly. So
this is
a very important point. So if you say you are T to the 5 and you are here, the prefactor is not clean limit prefactor. Your tangent here will depend on the limit prefactor.
Yeah, but then it should depend on the film thickness, for example, in the thin film samples. And to my understanding, at least for aluminum, the prefactor is essentially constant in experiments. At least my knowledge is from 20 years.
It will depend on film thickness if it's smaller than mean free path. Yeah, so if it's bigger than the mean free path, then it's bulk mean free path.
But in aluminum, at least films typically the mean free paths. It's like in bulk, it's like nanometers or so, and then typically thin films that were used in those experiments get below.
Do you have a reference?
This is a recollection from sort of collaboration with Pekola. So they, unless they always use the same thickness, that it would be slightly surprising if.
Okay, good point. Thank you.
So, what is maybe to add another question to this? What is surprising for me is we often use copper absorbers that are pretty small, smaller actually than the phonon thermal wavelength. It turns out that this T to the 5 plus minus delta law seems to work very well, and it's really not clear to me. It's always been a mystery why it works in structures that are smaller than phonon wavelength.
Smaller than phonon wave. So you have piece of copper and sandwich between other metal. Exactly.
So electron-phonon coupling can be very well described by the same laws that we find it really works nice. But if you think of the size of this acoustic phonon, it should be more than a micrometer. It doesn't fit into the box. So.
Well, but you don't want to say that your phonons are quantized and have discrete spectrum. No. So they are leaking. So you still have sort of, so your phonons maybe not plane waves, but it's a piece of, so you still have continuous spectrum, you still have extended phonons.
You're saying that if the transmission between phonons is quite transparent, right? From the substance, which is this from what I remember. And they're well coupled essentially. So the only mechanism of relaxation for those phonon is in the metal. You're only seeing the metals, even though they mostly live in the substrate.
They mostly live on, yeah.
Yeah, it's probably.
Then these parameters are probably more substrate driven than depending on really
Because this is the electron-phonon interaction. Right? All this knows about the electron-phonon interaction in the metal. The time scales. Yeah.
But you need sort of phonon density of states, local, so your phonons are kind of scattering states, but you need local density of states.
Yeah, but this is kind of an overall factor, right? It will not affect.
If this phonon density of states is frequency dependent.
Yeah, no, but I'm saying that, for both the clean part and the disorder part, right? It will change your integrals, I agree.
Yes.
Right? But it will change the integral in a sense in the same way.
Okay, because it has nothing to do with electronic in free path, so
Yeah.
Yes.
Sorry, maybe I missed it. Question with so it's only the crossover temperature that depends on the mean frequency?
Well, the prefactor also was the prefactor here.
Okay, the prefactor for
The prefactor here does not depend on the limit because it's we covered the clean limit. The prefactor here, of course, does depend.
But so if I understand, nothing really depends on the photon transport.
So here the phonons are assumed to be ballistic plane waves,
Infinite ones, even if the region is very small, even
Yes.
if there are the reflections.
Yes. Yeah.
But is that true for very disordered medium, like you are talking about?
Well, depends on what is disorder. Like if you have disorder which works for electrons, but for phonons is kind of averaged out. For phonons, in free path diverges above. You have like power. For impurities move with the lattice. So at low temperatures, I think phonons should not be very much affected.
and that's thermal phonons, right?
These are thermal or whatever you emit. Like you can have a quasi-particle which is at a bit higher energy. You can have zero temperature for phonons, but this quasi-particle can emit a phonon and relax.
No, but if, for instance, if you shine a lot of light and you somehow fabricate non-equilibrium phonons, no?
Yes.
And then
Well, then you don't have any temperatures. Then you have to solve the kinetic equation, and this is not applicable at all. So this, of course, assumes that you have electrons which equilibrated among themselves. So they have electronic temperature. You have phonons that are equilibrated. If you are something in some transient regime when you have relaxation cascade, okay, that is totally different.
No, and also it's the other regime I was asking this morning. That if you also, are probing a resonator strong enough with a lot of photons in the resonator, then you can also drive both the electronic system and the phonon system out of equilibrium. Then you get into this regime where you have to solve the kinetic equation and so on. But it is still based, the kind of steady state you reach on this kind of argument. So it's still a question of, what do you put in for your matrix element for the phonons? So it's related to this, in the kinetic equation.
So when you write the kinetic equation, you are facing the same question.
That's a theory point of view.
Yes.
I mean, maybe it still looks the same in practice for experiments. You compare the theory that you would do in the this kind of quasi-equilibrium regime, the theory that you would do the non-equilibrium regime, and then you compare that to the experiment, that maybe they look almost the same.
Yeah, especially if you don't have many decades in your parameters, you use your prefactor
Yes,
as a
yes.
heating parameter.
Yes.
Yeah,
yes.
so that's my point here, that in many cases you can actually, you cannot really distinguish and claim that one is much better than the other if you don't have more than a decade in temperature. Like instead of T to the 5, you put to the 6, but you choose a little bit different sigma.
No, what I do know is that this was done a lot, at least in Pekola's group, that they tried different exponents and simply they didn't work. That's why they chose 5. About this prefactor that I mentioned, we actually in the same review where we wrote that statement, there's a table of prefactors for different materials. I wouldn't claim that they hold to more than 1 digit only. That's another magnitude. So if they change by a factor of 2, maybe it's not a major thing. So your suggestion might still be kind of somewhat correct, but it should not be like. I would be surprised if they would change by a factor of 5 if you make it.
Because from an experimental point of view, getting more than, I would say, 2 orders of magnitude for the temperature is quite hard. If you start with a PC of 1 Kelvin, we're not going to go below 10 milliK. Like even that's the.
You don't have to be in superconductor review, yeah. So you can.
We can go up in temperature as well.
Well, for copper.
Yeah, of course. But is there another way to probe the same mechanisms?
Yeah, this time relaxation, this relaxation time what we saw this morning in the resonator is also proving the same. Like it's the electron-phonon reduction, superconducting carrier, again, this thing. And again, is this question whether you have 7.5, 9.5, and so on. But then it is again the same problem, right? Can you really explore as many decades? Also, because actually that is also an approximate expression for low energy quasi-particle at the gap. So you don't have that much space also in energy. Right? Because you are limited from below by the temperature essentially, because at some point, your phonon will excite also the quasi-particle, and you're limited by above by essentially the gap. So again, you're sandwiched in between those two, and then you will change power. So yeah, so I agree. I mean, experimentally it is, but it's kind of work, right? I mean that, so the question is also what, as a theorist, if you want, right? Your experimentalist comes to me with some data, and then you try to fit it. What do I put to it? 5, 6, 7.5, 9.5. I mean, everything seems to be working, so it's not clear also to me. I mean, why? Indeed, if there's a way to really discriminate, I think it's different. No?
The graphene is very different.
Yeah, actually, yes, but probably the way to get the most, like take copper without any superconductivity, then create a photoexcited quasi-particle. Well, the real cutoff is dBi.
You still have to be well below dBi.
Yes, that for sure. You have to be well below dBi. But if you are so you can start, I don't know, from 50 Kelvin. From 50 Kelvin you go to 10 millikelvin, and there you can. I mean, there you for sure will get both clean limit and diffusive. But then you can try to fit the whole thing. Just don't fit with the power law, but fit with the same with the full electron expression.
Yeah. So I think experimentally it would be hard to go very low in temperature. I mean, now we know a bit better how to do electronic temperature.
For thermal transport, then it becomes delicate to subtract the phonon contribution from the electron-phonon.
Miguel, when you tried to different powers, it was pretty clear that one was working and not the other, no?
Yeah, 6 were working, not the other. But I think that this is because you have few orders of magnitude change of resistance also. While here it's a small change most of the time, no? It's like if you have a clear switch of some order of magnitude.
Change of what? Here you have a decade and a half in temperature, but in conductance, because it's high power, then you have a lot of decades. So you need a decade in temperature, I think.
Okay, but then I think the system is even stranger, right? Because they're insulators.
Yeah.
It's even a weirder situation.
Yes, and all this, of course, yeah, this theoretical,
This is metal.
it's diffusive or clean, yes. Well, insulators, there is Kravtsov Feigenman.
This is kind of supposing that you have one electron-electron, right? This kind of assumes that the electrons stop in each other.
You have like electron-electron interactions, which are fast, which is definitely the temperature for electron.
When you move away from the clean limit and towards disordered stuff, does that fall?
Depends on the situation.
Thank you.
If you go close to KFL, close to
Oh, but then all this breaks down.
No, but what is true is that you have to be able to define an effective electronic temperature. So the electronic temperature is not the one of the bath, the phonon, but still you assume that you have Fermi-Dirac distributions. And if you are completely out of equilibrium, then none of this works.
Usually, you can think in terms of time scales. So the dwell time of your electrons is larger than the inelastic interaction time of the electrons. Then you could assume that you have internal quasi-equilibrium with the electron, but this is not necessarily correct.
But what I meant is when you're okay, so this is going to tell me that this is not going to work. But if we're moving towards a localized regime, then you can assume that you don't have so much electron-electron interactions, or if there are, then there are other problems from the transport point of view. For me, it's a question. It's a trivial question.
So why would you get to achieve report 6? You have seen this many things.
I don't know.
Because it's a clean
Why
no.
not?
It's not even like
It's new,
When you are in the insulating regime, electron-electron interactions are always there and they thermalize. But one electron can jump in one grain and the other in the other grain. This is a long-range interaction. So this is far more robust than anything else. Thermalization by interaction is always there, even in the very insulating regime.
Even if you're localized?
Yeah.
but you thermalize to
This is,
buff in this case, no? You still need something thermalized.
But if you don't assume metallic weight, you assume completely localized weight factors, okay?
localized within a grain, I understand.
Then
So one electron jump from within a grain and the other within the other grain, but it's a 1/r cube interaction. So
yes, but you have to assume like an existing metallic grain.
yes, yeah. Okay. I mean, you have to assume that many wave functions overlap in the same region so that you relax within that region. With a 1/r cube interaction, interact with the other region of thermalize.
In the linear response regime, this electron-electron thermalization doesn't even matter. So if you now here is the kind of the power. You assume that the phonons are at 0 temperature, and then you just change the electron temperature. That's kind of the far from equilibrium regime where the thermalization matters. But you can also consider the linear response regime where you are changing the temperature only a little bit, and then looking at the heat conductance. Then actually this electron-electron doesn't matter at all, but you can still probe this temperature dependence of this heat conductance, at least in theory. And there, okay, then you have a sixth order power here, the heat conductance code fifth power.
Yeah, this is. This is probably why you get this huge temperature. It's easier to measure linear. Okay, let's switch to the next question.
Okay, so that would be again, this is not.
Okay, so you can press.
Okay, so hi everyone, I'm Eamon Speaker now. I come from thermal detectors. I'm more interested in thermal effects, temperature fluctuations, temperature, heat conductance in nano devices. So I use superconducting junctions as probes of the temperature, but I'm not really looking at superconductivity itself. But I think concerning relaxation processes, I think there's interesting common grounds to this. And yesterday, when I listened to the panel discussion here, was this question: what could be sort of new probes of looking into SIT or this? And it came to I had this idea that got trivialized by the talk of Peter this morning, which is that actually looking at real-time fluctuations of things would be very interesting. So I want to show a few things there and hopefully trigger maybe I don't know, new ideas in relation to this. So the idea is that we can, it's possible to measure electrical quantities in a very fast way by embedding them into RF or microwave resonator, like what we have seen this morning for measuring kinetic inductance. And if this, so in our case, it would be, for example, a Josephson junction. So we're not measuring a kinetic inductance, but a Josephson inductance. And if the critical current depends on temperature, then this is a thermometer, and this can be probed by RF. And it has a very fast response time. So we can measure this with 100 nanosecond time resolution or even better. So typical experimental configurations are like this. There is an absorber, so something that is picking up heat. We have on this absorber also a thermometer. All this is in galvanic contact. And then we measure, we can convert our measurement there into a temperature signal. Then we see them. So here, for example, it's what I show on the right side is a phase slip in a Josephson junction that translates into a heat spike. And then you can see the magnitude of this heat spike and its relaxation. So you see that here it's a metallic absorber, and typical heat relaxation times in metals are microseconds, several microseconds. So it's shorter than in superconductors. We've seen it this morning that depending on the combination process, it can be pretty slow. Okay, so now I'm going to try to introduce you how this works. So it's just that you put this into a resonator. It's not very important. For example, this morning we saw in the talk by Miguel that you can have bistable situations switching between two states. So this really reminded me of something that we also measure. So in an SNS junction, you can have thermal bistability. You can go to an overheated state and then retrap back to a cold state. So this is really analogous there. And here in this experiment, I'm not going into details, but we can really measure in a time resolved fashion that the system is switching between hot and cold. So I think I would find it cool in some, maybe in an insulator, this could also measure in.
This is the equivalent in the washboard model to say that your phase will done with refract, done with refract.
Yes, you could think of this, although it's debatable whether in an SNS junction we can really use an ICSJ model. But yeah.
Why would it stuck in a kind of heated state if you're talking about a good superconductor? What's the mechanism here?
I don't know. That's an open question. It's just we see that it goes on sub-millikelvin time scales. So it goes to a hot state, then it's dissipative, and something stops the phase from running away, and you're trapping back into a cold state. So this only works, doesn't work in very low temperatures when you're hysteretic, then these two are very far apart. But here we went to just at the crossover where rejumping and switching current superimpose. Then you go into this crossover, and actually by looking into the detail, you see that this smooth looking curve is actually, if you measure it with the time resolution, you see that it's really bistable. It goes back and forth between two states. Okay, so now I want to sort of react on what we said about electron-phonon coupling. So here is yet another system. So it's two-dimensional germanium. It's in a heterostructure. You have a two-dimensional whole gas in there. So this is grown by epitaxines. So it has long mean free paths. It has pretty high mobilities when it's conductive. And we want to use this as detectors for other things, essentially for reading microwave radiation. So it's similar applications as Peter's talk. And so we made a heat balance on this. And so in this material, we found a power law that works well. You see, it's also a finite, quite a finite range of powers and temperatures. The problem is that actually no thermometer works well over several decades in temperature, and the same is true for heating. Actually, you start to get different dominant heat leak mechanisms at different temperatures. So this is why it only works in a limited temperature range. What we found there is 3.5, and this is exactly what people have reported in bulk germanium. So that came like a nice coincidence. Then discussing with Dennis, I mean, there's also superconducting half there, and I mean 3.5 is also 7.5. So maybe some temperature relaxation is happening actually in the superconducting weak. So this is an open question to me. But just to show that, okay, in other types of systems, you have other types of power laws. Now I have an open question there. So we can, just as was discussed earlier, we can look at temperature relaxation. So actually, this is not in the linear response regime. So it's more complicated than just an exponential. Okay, so but it works pretty well, and down to even very low temperatures, 10 millikelvin. We can just fit this using, I mean, by solving the heat balance equation, where we put the power and the variations of the internal energy of our absorber. So this works quite nice. So this is in a regime where the germanium is rather well conducted. So there's lots of charge carriers. And now what we saw is that when we are going, so we're increasing the gate such that we are approaching the pinch off. So your device is getting gradually insulating. And the observation that was, for me, unexpected is that the relaxation time goes down. So it comes quicker back to its initial temperature. So I don't understand. So this is an open question I put on the table. And I think it is probably connected to things that were discussed here.
I have a suggestion at least for this. We studied a similar thing in graphene with Bertti Hakonen, where they also studied as well how this relaxation. Actually, the idea was to study use sort of superconductor graphene superconductor junctions, measure temperature in graphene and measure the Electron-phonon cooling there. And we realized that they didn't actually measure that, but what they measured was the diffusion to the superconductors, even though they were studying the subcap transport. And they noticed that actually this diffusion effect depended on the conductivity, or actually the graphene sample, which you can then vary by with the gate. And the mechanism that we identified for this was actually that it's a kind of electron mediated sort of transfer of energy to the superconductors. Because you have electron collisions, what happens is that sort of sometimes these electron collisions take kind of the electrons out kind of from the thermal window at first, and then sort of if that happens, then they can decay to superconductor. They can go above the gap, and the strength of this effect kind of depends sort of on the resistance. The higher the resistance, the stronger this effect. This you can show by a detailed kinetic equation analysis.
Resistance or the
resistance
of
internal.
graphene?
Resistance of graphene. So and it kind of the relevant scale is the quantum.
And this would work, although the temperature is much smaller than the superconductor. Yeah.
Okay, this is 2011 paper, so I had to remind a bit how it went, but kind of the idea was that there should be like an Andreev blockage from superconductors, and therefore no diffusion of superconductors. But this Andreev blockade didn't work because of the blockage. So yes, it works even at low temperature.
You need to conserve the total energy, right? You have electron-electron collision. If your total energy of the
you would think so, but actually
delta you cannot.
Actually, it's not quite true because you twice put it. So the electron is supposed to conserve the total energy, but it can actually, and this is kind of locally it should, right? But now in this mesoscopic setup, sort of it can assist the diffusion process.
Yeah.
Then it.
Where does the energy come from to overcome the delta?
It doesn't come anywhere, so it just sort of changes the conductance to the superconducting leads.
So essentially, you're extracting energy from the heat bath in the graphene.
Yeah. So here the idea was the same as the industrial experiment. The idea was the same here that you want to measure the electron-phonon coupling by kind of putting a bit of heat and then using the SNS to detect the critical current to detect the temperature. And then sort of analyzing how the kind of measured temperature depends on the power you get the heat power out. And what we found out that it was not because of phonons, but it was because of diffusion to leads. And this diffusion to leads was assisted by depending on the resistance. Paper 2011 PRB by us.
So maybe you lose the effect if you're at high enough temperature.
Are you sure your absorption coefficient is the same? So you're tuning the carrier density?
Yeah.
Are you still absorbing as much?
Well, it doesn't really depend on this. Because you're just bringing your system out of equilibrium, and it doesn't matter by how much, because you're just looking at the time scale.
I think you were saying it's not exponential. So you have multiple processes, so it's not exact.
Yes, but still, I think that if you look at the bottommost curve and the topmost, you'll not the same. In one case, it's instantaneous, and in the other case, it takes a microsecond.
About the graphical states, because in the time you have also.
So yeah, well, in a 2D system, in principle, the density of states is constant, and the heat capacity is also constant. As long as you're not approaching, I mean, it's really a one person.
Yeah, but if you have subleafing, so you have
exactly. So when you approach the threshold, then disorder will take over. So I think
your density of states is no longer constant. It's small. I don't know because you can go towards the right area from your density of states. Which means the time will be short.
So just for me to understand, so that exponential is a such exponential, so the equivalent of a diffusive media. How do you describe it? The exponential like behavior?
So okay, so if you have this power law, this beta you can linearize this. If your delta t is smaller than t, then you can linearize your power law, and then you get a first order linear differential equation, and then the solution is an exponential. But if you are not in this regime, then it's a bit more complicated. Don't have an analytical.
So maybe I have a question related to 3.5. So if you do the same experiment with SLS, get t to the power 5.
Yeah.
So why here germanium would be 3.5?
So first of all, it's two-dimensional. So I have no experience with, but I think in graphene, typically it's also something that around 3 that is found. If I remember well.
Graphene is complicated because there's both Dirac dispersion, which gives you some matrix element issues. But then actually disorder there leaves those matrix elements, so that there is a supercollision mechanism. Then it depends on whether you are close to Dirac point or away from the Dirac point. And it's pretty complicated. Their disorder does actually play a strong role and assists the component coupling because it gives kind of phase space restrictions that you have it.
But as soon as it's conducted, it's pretty good conductor. Mobilities are 100,000. So this is also very good.
Dimensionality is pretty simple. It just removes. I mean, if it's an ordinary metal but just 2D, then it just lowers the exponent if I write by one, I think. But it doesn't give you 7.5 directly.
Just as a comment, so we did some very preliminary relaxation measurement with this here, and the same those that were very isolated in the profile, and we have a longitude dependent. I don't know, Johnny, if you time relaxation, changing the voltage, waiting for stuff to change, or looking at the evolution of. You didn't say anything?
I think all of us, I think like you said, that great.
Let's go. Maybe we move on to aluminum. I don't know if it's change seats or should I just.
Yes,
You have really, yes, the logical just this slide, so I can switch whenever.
This is the second one. Let's maybe go to the first one.
So this was the second.
Yeah, this then goes back again about this question about time scales and interplay where you can resort and electrical interaction and so on. So I'm just showing some, for example, some data there that was made by you and Bob. And it was just measured, essentially monitoring the response of granular aluminum meters. And you see that every few tenths of seconds something happens. This is probably like the cosmic rays in the substrate. But the thing is that also you see that the recovery is very slow. Here is even seconds. So this is much slower than in homogeneously disordered superconductor. If you take like aluminum or like also we saw this morning, is more like in the milliseconds. So there's like orders of magnitude difference. And one question, that is a bit related is that even if you have these rare events that generate quasi-particle, very rarely, but then your recombination also become very slow, that this lead to excess quasi-particle and excess dissipation, as we were seeing this morning. That could be a mechanism. In fact, there was theory that was worked out in this paper by Nazarov, Jose, and others, in which they said, that if you have this in this disordered superconductor, you have these subgap states. So there are a few, because of inhomogeneity, the quasi-particle can get trapped there. And then their argument was, okay, if something generates a quasi-particle, the quasi-particle relax into these localized states, then they cannot find each other, right? They will be stuck there, and the time scale to recombine will be extremely slow. And so there can be a crossover between a regime in which if you have a lot of generation, essentially every time you add a quasi-particle, they will find a companion, even though it's localized. And so it's back to the regular, if you want, like Rotvar-Taylor or mean field regime. But if your generation rate goes is slow, right? They have this bubble picture in which, okay, you generate a quasi-particle here, it localized, but if it by chance happens to be nearby an existing quasi-particle, you will recombine. But otherwise, if it's far from the other quasi-particle, it's stuck there, it cannot recombine, so you get kind of steady state again, but in which there are many more quasi-particles than you would expect. So this is one possibility. Again, you have this rare generation, but if the quasi-particle localized, you can get this excess quasi-particle. So that's one possible mechanism. But if we so we looked a bit again in this, at this approach, and we found out that it also depends what you mean by fast localization, right? Because again, the first step was that the quasi-particle has to go there, localize, and then it's stuck there and it cannot recombine. But if you, before going there, it can find something else, like there are other mobile quasi-particles and so on. So in fact, what we said is not only one parameter that determines this kind of dynamics, there's a second one that tells you, are you in this fast localization regime or not? Then you get this kind of diagram that I'm showing on the top. But this discussion, the important thing is that even if you assume that you are in this regime in which you can get this recombination and this excess quasi-particle, we can put a bound on that depends on the ratio between the localization rate and the recombination rate. It will, bound your quasi-particle density. And then what we find out that if you use this, for example, 7.5 again, so there's a bit of dependence on this power there. For example, for aluminum, we find that essentially, even in a relatively large planar wave like resonator, you have less than one quasi-particle in the whole volume. So we conclude that, for this type of devices, so regular aluminum, this mechanism doesn't play a role. Because even if it plays a role, you have maybe one quasi-particle in the whole volume, so you don't care essentially. Of course, the situation might be different in different material. And we saw already this plot this morning, right? It was in Peter's talk. And so what I wanted to point out is that they say indeed that, for aluminum, they find, is this like blue shaded region is where these aluminum devices are, regular aluminum. And it looks like indeed the losses are limited by something else, probably two-level system, genuine two-level systems. But indeed, if you take other things like granular aluminum or malleable nitride, are in this other region of the diagram where it looks like this localized quasi-particle, and indeed this slower combination may play a role. There is some discussion, and that's why I was asking this morning about beta tantalum, because in this plot is also in that region, in this red region. But I had some estimates that says that this should not happen because again, if you remember, TC is similar to aluminum. And so again, even if the disorder is a bit stronger, so instead of this 10 minus 3, maybe it's a 10 minus 2, then of course you have this power law and so on. So it might go up. There might be some quasi-particles around. If I only look at this estimate, so instead of 1, maybe I have 10,000 or something like that. So it's, it could be, 1,000, it could be still a significant number. But the problem is that, let's say you're measuring at 10 millikelvin, and the depth of this trap is for order 10 millikelvin. So the phonon can also kick out the quasi-particle. So again, you're still in a regime. I'm not convinced, for example, that this is the explanation for beta tantalum. So that's the kind of question. So that's why it's back to the question, okay, what are the energy scale and the origin of this trapping mechanism? Because, even from this kind of analysis that we do in this paper, is not clear to me that is a definite answer. So that's the question I have. I don't know, you have any other insight?
It's the same question we have as well. This energy scale is the only thing that doesn't add up. And yeah, so look, might be something else going on than just electronic disorder in samples, right? Could be some oxidation, but then again, for aluminum, that's also the case. So yeah, it's not clear, I'd say. So I think, I had this question for I think a year, and this is a very well posed way. But the energy scale is the only thing that doesn't add up. That's the thing. So if there's some other way of trapping these quasi-particles with higher energy scales, they would add up in the same kind of number order as well. So yeah.
Not that big. Oh, sorry, maybe you.
I was wondering, so could you do the same experiment on granular aluminum that you did?
Yes, we could. That would be very nice. But you have
Maybe we expect some variation of the temperature significant. And also electron-phonon coupling is different from which actually would, well, for small gap, maybe reduce electron-phonon coupling. Very speculative.
I mean, again, there is some evidence that, again, in the previous slide, right, that these timescales are much longer in granular aluminum. Now, a precise theoretical description is lacking as far as I know, unless somebody knows. But the experimental evidence is in that kind of direction, that they are trapped more strongly for sure compared to regular aluminum.
So I tried to propose another mechanism of generating this excess of tiny particles. So, but what do you think of this proposition?
Yeah, I was not sure. I mean, actually, if I understood correctly what you were proposing, so that is also an open question if you want. Because I mean, I understand. I mean, there are these, like the subgap modes, but these are more collective modes. So what kind of roles they have with the generation of quasi-particles is not.
Yeah. Okay. So they are collective modes, but then when you put some currents, if we use semiconductor, you decrease the superfluid density, and somehow, when you do that, you increase the number of particles. I don't know exactly where they are in terms of energy. If you can try with but still, I know that you have an electron conservation. So you decrease the superfluid density, you end up with more particles. And just I was suggesting that this quasi-particle will originate the dissipation.
Sorry, can anybody explain to me why decreasing superfluid density means increasing the number of quasi-particles?
Okay, to decrease the number of electrons in the condensate. So where this electron?
Well, you can just increase your disorder.
No. She's talking about, when I think, sorry, maybe I'm wrong, but because she was, for example, in one experiment, you were exciting like a higher harmonics, right? So she's driving current through another mode and then measuring the response of the fundamental. And you can see the effect, which is some kind of cross-current in some sense, maybe, I'm not sure, but.
Cross-current, yeah, it's basically cross-current.
Quasi-particles for this, you have some nonlinear process.
Yeah, so that's the question, whether I'm not sure whether it is directly telling us about quasi-particles or not.
Okay, and then what happened to
There's the current that you are flowing is approaching I star, which is IC, which is proportional to the density. I think says is that this density is, when this density is lower, you have more quasi-particles.
Yeah. So what is for sure is that when you put current in a superconductor, you start to decrease gap, start to decrease the temperature, and you decrease the superfluid density. So I don't know. I did not find any paper discussing on where these electrons that are not in the superfluid condensate anymore, how would you describe these electrons? Unpaired electrons that
if I think I have a vague idea of what you are talking about. Probably you're referring to this the superconductivity version of the sum rule, right? Essentially.
The superconductivity versus what?
The version of a sum rule. It's I don't remember the acronym.
Well, yeah.
That's the weight of the oscillator sum rule.
Yes, but with the superconducting weight, right?
Yeah.
Then essentially what you are saying is that where those excitations go, is this your argument? Then I would say, well, I'm not aware of what happens in diffusive superconductor because I've never conducted a calculation. I know that, let's say, in a strongly disordered business, where there are no quasi-particles, it's a completely different question. You can transfer these excitations to high energies. And I can argue that this is exactly what happens because from my theory, I can extract both the superfluid stiffness and the low frequency dissipative conductance, and integrate in the latter, I don't get the defect in the former, meaning that the defect has to go to higher energies.
Yeah.
And this, I think, is what happens, might at least happen, and there's no contradiction. So your electrons are just somewhere smeared around in higher energies. And that's
No, they are just because you got quasi-particles. And that's what.
Yeah, but this is a statement about the density of states, right? It's not, it doesn't mean that those states are occupied, at least not.
Yeah, so that's the way I understand it. At least. So current changes density of states, and changes maybe how this sum adds up, but doesn't change the quasi-particles per se. Okay, if you have a AC current, then these photons of this AC current can excite quasi-particles, which can have higher energy, can excite more quasi-particles. Okay, that's a quasi-particle picture, but apart from that, there's this density of states effect, which is the effect I think you are referring to, which means that it's just two separate effects. At least that's how I understand.
Yeah, so actually, there was a work, I don't remember now the authors, but Rafi was involved.
Yes,
we're looking at this effect of the on the change in density of state due to the AC essentially signals. So I agree that in principle there are these two mechanisms. They were claiming that they were explaining some experiment this way, some frequency shift. What I remember was that I think they did not include the getting back some fraction, so they were off by an order of magnitude of 2. And when we look at other experiments, it's not clear, but I agree that in principle both mechanisms could be active, but the interplay between the two, as far as I know, is not clear. So that there is one work or two that I know about this effect on the change of density of state with the AC, driving of the resonator. I know that's much more on the quasi-particle side. We did argue that maybe again in fitting some older data from Clafley and you, I think you were also involved. That maybe, from the frequency shift, it looked at maybe both mechanisms might be relevant because they might play like similar role, but it's not, as far as I know, there's no clear answer whether this is the mechanism or whether, one should account for both. But the thing is that if you look at the dissipation only, as far as I know, I would say that older experiment, again, with in not two disordered superconductors, this does not play a role. So it might be a question of whether you need a certain amount of disorder to be able to see this.
Or you need to have, yeah.
So maybe in connection to this discussion, I'm actually wondering if there's, let's say, a smoking gun way to actually determine the dissipation mechanism, and specifically localized versus delocalized, because as far as I can tell, if you're looking at dissipation alone, it is really hard to tell whether the exact nature of those quasi-particles, unless you have additional theoretical background of why like simple delocalized picture is excluded. So,
so I think actually there was already, I don't remember seeing some previous talk, people were asking, okay, we might need more local probes, right? Because this kind of like more, global measurements, indeed, it might be hard to disentangle different mechanisms that are playing external. But going back, you were asking about also energy scale. Of course, there is the possibility that if you have a lot of magnetic impurities, they form a band well below the gap and so on. But then you probably, see this kind of thing. I mean, if the material is not pure enough or whatever. This is something, these were also, it's similar, there were this related question a long time ago about the differing time, right? People saw saturation as a function of temperature, but then it looked like it was like part per million or something of magnetic impurities. But because that is very sensitive, but here you would need a lot of magnetic impurities to create this, band well below the gap.
Yeah.
So I don't think that's the explanation.
No, we don't have any indication that this many magnetic impurities. And there's one actually, maybe 2 points. The to see that it's really quasi-particles, at least for the higher temperatures in our system, we can do with this fluctuation measurements, because this variance really relates to the number, the density of quasi-particles. There, it's easier to disentangle this other effects. And the other point is that there's one more experimental fact, at least in the MKIT community, is that the dissipative response and the inductive response, they don't match at low temperatures. That's these temperatures that this seems to start playing a role. And that suggests that if it's localized quasi-particles that does this, that these quasi-particle states are not dissipative. And then they should be at least that's my understanding, at least h bar omega below the gap, because otherwise they would absorb a photon and dissipate this. So that's, yeah, I mean, that observation also hints at some bands somewhere far in the gap. But then again, what the microscopic origin of this is really, yeah.
I guess I think we did, but I know that depending on the growth condition, you can have tiny alpha tantalum inclusions in beta tantalum. Could it be sort of origin of this localization, and would they have the right energy scale, squared? So there would be also superconductor, much lower, his is unknown. So what's the energy scale you need?
Alpha is higher.
Yeah. The other way around. Oh, is that the other way around?
Yeah, alpha is like a 4 Kelvin.
Okay. Maybe it can work also.
But I think it was also important to sort of separate from our experiment, at least, the question of where the excess quasi-particles come from at the lowest temperatures versus what governs the recombination dynamics, where there is clearly a thermal number of quasi-particles. And that's where it's separate from where you can still invent other explanations, such as these collective modes. They do explain probably indeed the excess quasi-particles at the lowest temperatures, but not necessarily the dynamics of density of quasi-particles that is still reasonably thermal at somewhat higher temperatures, where we also don't see the recombination, but the scattering sort of lifetime and this other weird dynamic.
So maybe this is something I misunderstood in your talk. So how can you be at thermal equilibrium if you don't have the expected recombination to get the scattering this time? Is it because you have a very dilute number of quasi-particles?
Well, yeah, it's at relatively high temperature, so there are lots of quasi-particles there. And the assumption is that all these get localized up to like 400 millikelvin. And then if they're localized, they need a scattering event to combine. But this is, I mean, I agree that this doesn't align with this theory of Pascal and in precisely this energy scale. For the rest, the picture is exactly the same.
But even, I mean, just to comment is that even if you go into like weakly order, you know, like regular aluminum, you can have the number of quasi-particles still be thermal if your generation, you know, in this higher temperature regime, like I don't know, 150 to 100 millikelvin, because essentially all the generation you're overwhelmed by thermal phonon. So even if you have some other disturbances, they don't really generate quasi-particle. So the number is the thermal one, but the distribution and then the dissipation can be different. This is seen in the power response at the higher temperature. So you see that the Q factor or the frequency shift are different, although the number is still thermal. So you could have the variance that is still thermal, but in this time scale or whatever else could be different. So this is seen in this non-equilibrium regime. It's a bit different, but there are cases in which this is clear and understood. At least I think you understood. Others may disagree. But
if after relaxation of the quality factor, so how do you physically understand it? Sort of so dissipation goes down faster because maybe these quasi-particles are trapped somewhere, and then you still have a lack of Cooper pairs that you see in the kinetic inductance. So you see the frequency that goes slower, and then the quality factor actually I don't know, because in a vortex or in a normal region nearby, can this explain or not?
Maybe that's a question for you.
So there is one work that actually that is about non-impurities with this band that's in the gap. And then if you go to some specific region, you see that the dissipation is less. So this sigma 1 is because you trap these, or these quasi-particles are in this band and they cannot absorb microwave photon. So there is but I think, I mean, if you look at fine-tuning, yeah, this pretty fine-tuning to get there.
It's more in energy, let's say, than in space.
No, it's both in energy and space.
Yeah.
It's both. So you need them to be localized in space around these impurities.
Okay.
But this band also has to be separated far enough in energy from the gap.
But so does this kind of model quantitatively work?
No, that's what we were saying.
Oh, okay.
So we get so and you need magnetic impurities and you need the pretty specific concentration of that to have these quasi-particles exactly at this point where it cannot absorb a microwave photon, and this is this dissipation as well. So is it possible? But I think highly unlikely.
Why are you saying that so one impurity one should right?
Yeah, but if you created this band, if you want a band of localized states apart from the gap.
Okay, but if you have, it depends on the exchange.
Yes, yeah, it really depends on the exchange.
What if you have?
How many do you need? So suppose you have good impurity, that each impurity gives the state.
If you have a normal region, no magnetic impurities, but some normal region nearby, then it was particle go inside. Do you still see them in the superconducting response? Or just lose them somewhere?
Well, then you lose. If there is normal region, then it will just relax.
Actually, in QBT, the evidence is that they will help in the sense of trapping as well. This is right. If you do it artificial. Of course, I mean, again, this is a bit different because these are large traps, with also, it depends on the transparency because on one hand, you want to make it so that if they go there, they don't come back, right? But on the other hand, if the contact is really transparent, then you may have strong proximity and then it's not a normal metal anymore. So again, it looks to me that you would have to fine tune things, like a weak disinclusion R and a well, coupled R or not too well coupled to the superconductor and so on. So
in a microwave volume, you also still see this trap. So if it's too normal, then it dissipates like crazy, and it doesn't help at all. So in that sense, also the qubit experiment is quite different from this experiment in that sense that we probe the whole volume with the microwave tone. So we also see the normal regions in principle. Whereas with the qubit, you have a local probe, namely the tunnel junction, and you can have another local trap of quasi-particles, and they don't see each other, and just drag the quasi-particles away. So that's a neat trick for the qubit. But we want to see the quasi-particles, so that's the.
Yeah, it depends, of course. Yeah, also what you want to do, right? Qubits, you don't want the quasi-particle. On detectors, you want to see them.
Yeah, sorry, that's crazy, but.
So to this plot, actually, there are also these 3D cavities where it's well known that there's also some residual resistance, which people don't understand for a long time now. Would you say this is related to also the problems you're facing here now, or is it completely unrelated?
Okay, 3D cavity is also different. It's a very different situation, in the sense that, okay, so I mean, even from what I remember, even the paper they comment that they are trying to extend their theory to this 3D bulk cavity, although there's no really reason to do that. So, first of all, I'm not sure, if this should be taken too seriously. The first comment. The second comment is that from what I know, for example, what I remember is that, for example, in niobium cavity, a lot depends on the surface treatment. Because niobium has something like 7 different oxide, 5 different oxide, 11. I don't remember the exact number. There's a bunch of them. Some are insulators, some are normal metals, some are different conductors. So if you don't treat your surface, very carefully, you get a mess, essentially. So, but so for people that want to use them for accelerator, I've been, doing these things for some time. There is some evidence that you have also to be careful with bulk superconductor how you pull them, because if you trap residual field, in terms of whether it's vortices or like some laminar thing or flux tubes or whatever it is, doesn't even matter too much. But you might have also excess losses that because you have some small normal component that you were not careful enough to put down. And of course, screening a big, 10 centimeter cavity is not the same thing as screening a QD. So, I think it's a very different. I mean, there are related questions, but it's different because you might have to do with surface properties, while QD is kind of also case.
Okay. So this is a question which also has to do with quasi-particle relaxation, but let's say in a very specific way, which is related to what we have heard yesterday, for example, the Christoph, which is what can happen to quasi-particle relaxation in presence of vortex anti-vortex pairs, which is specific to these conductors. And why I'm asking that? So if you just consider quasi-particle relaxation in the context of some, let's say, regular vortices, I think this is rather well good. Capture a quasi-particle and then you fast relaxation inside the core and or eventually a recombination with another. So here I show some few papers which deal with that. This one I found this morning, which treats also the, I think the exponent, it's the exponent. So since it's supposed to be a normal core, we expect something faster. So this is used in so we're in superconducting resonator circuit for TIDES, but also for superconducting qubits. And so John Mucci is part of this paper. So here they show that if you manage to create a vortices into the capacitance of transmon, so you manage to increase the radiance of this transmon with bonds of quasi-particle. You try. So this is used in the superconducting qubit, and also this is used. And so my question is, what's happening if you use this superconductor like hydride or aluminum, so which has this function of temperature? You can see there's this PKT transition. But if you go slightly below, so this means that you have pairs with vortex pairs.
Back asking that you lift your voice.
Okay. So the question is, so in this systems, so it's not a single vortex which will suck quasi-particle. So these are pairs. So are you maybe? I mean, my colleagues were not aware of the experiment or theory about that. So are you aware of this? And if not, what would you expect? You expect something different, special?
So Thomas Jalabert doing his PhD with Paul Chapelier, one who did this STM injection of quasi-particle in a nanowire, put some magnetic field to have a vortex, and then try to put locally quasi-particles inside the vortex outside and see how this affects more or less the critical currents. Okay, it's not perfect, but it's in this PhD management in English. And as far as I remember, they were localized, they were trapped in the wrong spot.
But that's for single vortex. My question is what's happening for vortex anti-vortex pairs? So do you have cross section which would be different? So the capture of the quasi-particle might be different.
So I don't know whether the cross section is different, but what to keep in mind is that these vortex anti-vortex pairs are not static in a way, but like generational recombination processes of carriers and semiconductors, they appear and recombine all the time. So if you have a start with a vortex anti-vortex pair, trap some quasi-particles there, and then they annihilate, you set all the quasi-particles free, which are in the quarks. So
for you, that's more detrimental than something.
Unless they have had time to recombine inside the vortex core.
Inside the vortex core. It's a very small relaxation volume because it's only 10 nanometers or so, or 5.
Question: do we have an idea how long these excitations and relaxations take? So how long can this typical vortex pair exist?
Good question. I don't know anything about that.
Thing is that in my mind is probably really naive. These vortex anti-vortex pairs are always linked to dissipation. In a sense, like in 2D, it's like they're linked to the fact that you don't have a real superconductor, and that's like the logarithmic dependence of the resistance at total. It's like, in this sense, if you add dissipation to your system by using a 2D superconductor, it cannot be really a good idea in the sense of a resonator kind of thing, because you will kill the resonance.
Maybe as a function of temperature, you get this speed vector.
This is the
part of it could be related to gravity. This is just one mechanism in my abnormality. So I'm saying it's
in terms of what is your question, which is thermalization. It's like if you increase the population of quasi-particles, because technically a quasi-particle are linked to it, it's like you change the temperature, you accelerate the cooling down of it. I think that you change the resonance in a resonator, like in a mesoscopic resonator, but in a way your resonator may actually be faster, thermalize faster. But this is maybe a really naive way of seeing it.
Just so I'm not really familiar with the vortex anti-vortex, but I know that for normal vortex, when you add more disorder, you increase the pinning, and so they cannot move anymore. What happens for vortex anti-vortex when you have large pinning? Does it play a role? And maybe they are not dissipated anymore.
If you pin them, they don't appear anymore. So the pinning in this material is super weak. So magnetic resistance is linear, nearly linear, at least close to the Gauss-Lewis temperature, from 10 millitesla to 10 Tesla, because it's entirely flux flow. So I think if you have pinning centers, they may capture some vortices, so far so good, but all the dynamics is not governed by these pinning centers. And actually below the BKT, they're also not contributing to resistance because they are paired.
Yeah, below the BKT, they are paired. They don't exist. Which is
you see, this is most of the temperature range that you have there.
So you say that these vortex, anti-vortex, they are moving?
Below, yes.
So this means that compared to a single vortex, which is pinned, and the cross section can be different, right?
Yes, sure.
So they're moving, but they're not dissipating. And then, so the question of this young man remains. So maybe they live long enough. They can
flip something.
Yeah, they can flip something.
I have no idea what is this flipping or this combination generation dynamics. I don't know of anyone who has addressed this.
I think that's maybe an interesting question for the future to think how one could act with that.
Intuition will be heavily dependent on temperature, but yeah, it's nice to have the generation decomposition bits. And maybe for pinning, but it's a very naive picture. It's the same as quasi-particles. If you pin them, they will recombine faster. Trap and pinning, and for semiconductors, it's the same. You have resistive declination of electrons on a wheel. It's a nice general analog. Maybe it's false, but yeah.
Would be one of the partners is pinned, and then the other recombines faster.
Possibly, yeah. Possibly, yeah.
Good. Lots of new questions.
Actually, Christopher, is that the time, the lifetime of vortex anti-vortex technically is theoretically known, but I don't think that we need a measure.
No, I don't know.
Yeah, so it's like probably it will give you like an evolution of the lifetime in the resonator, you know, but you may be able to measure, but I'm not sure about it. Like I don't think that we never measure, but theoretically at least it is a known quantity.
I mean, it should be possible to calculate it. As far as I understand it, these vortex anti-vortex pair work like a marble in a or am I wrong?
There's something for this friends of time independent called Landau, maybe they should make that.
And Julien, we were expecting this recombination time to be non-monotonous with temperature, or you say something about that?
No, I just say some extra. I mean, so you normally activate these vortex anti-vortex pairs. So helps, let's say, catch the quasi-particle. So if you catch the quasi-particle, maybe your QI, which is a bit increasing, and then also too many.
Above a certain density, they will recombine fast or not.
But again, I think the point is indeed whether they're mobile, the vortex can move or not. So because for this, you know, for really to be helpful in trapping quasi-particle, you want them to be pinned, essentially, because then the quasi-particle will get there, relax, and then you don't see them, at least for the qubits. Again, the global measurement will. For the qubits, it helps because they're trapped away from the junction, right? But if the vortices can move and they unbind, right, they give you more dissipation. And actually, I mean, even in the qubit themselves, we saw this kind of effect that, you know, because they're probably the pinning is kind of weak, so it's more like a geometric localization in that case. This is relatively thin aluminum, so you add vortices one by one in these paths, right? But one vortex will not add much dissipation, and it will help more than it hurts because it will indeed, you know, help you relax the quasi-particle. Well, at some point when you have too many vortices, I don't remember the number, whatever it was. At some point, the dissipation of these non-pin vortices overwhelm the advantage of capturing the quasi-particle, and one goes down. The qubit, it is non-monotonic, but again, it's very different from resonator because you're worried about the quasi-particle can you know, go across the junction. So if you keep them away, it's fine. But on the other hand, you can, you know, if the vortices move around, essentially they give you ohmic losses. So your capacitor become also lossy. But I think in resonator you do not see this because if your vortices are moving around, they will just give you dissipation.
So what we have observed is that, say, the quality factor of our relatively bad resonators starts to go down significantly already half a Kelvin below the constant Stardust temperature. And so the qualitatively understand is I just thought that the AC signal just move them, they are bound, but they are oscillating in the AC current, and that produces additional dissipation, even though there is no voltage or the contacts.
Yes, exactly. Yeah, it's more AC absorption by the vortices.
So the goal of the vortex is to have a quasi-particle, right? Like somewhere like.
Well, I mean, there are two things, right? I mean, you want to pin them, not to have this flexible resistance, also for AC response, right? Essentially, I mean, if there are vortices, you want them to be stuck there for both cases. I mean, if you want to have low dissipation.
There is movement of vortices, and there is the fact that you want to have a place with quasi-particle in the system that will also
yeah, it could also help trapping. Yeah, but again, you know, if they move, they will. I think that in most cases, if they move, they will not help you. Again, the qubit is a bit different because you're probing locally the density near the junction area. When in the resonator, you see. So I think there was an experiment around the same time in Riton group, in which he played a bit with the geometry of the resonator to make sure that vortices were only in a certain region of the resonator. So you could see the effect that if you had like even harmonic, it would be insensitive to the or odd. I don't remember which one it was, right? But if something had a node there, you would not see the vortex, and something with a peak. The response would see it, and he could see the difference between even and odd harmonics. But he would only get this paper. Yeah, I think it's that. Yes. But in this case, I think they could only hurt. If I remember correctly, I might be mistaken, but.
Okay, so well done. Thank you very much for your participation. It's we always come 2 hours. So thank you